Welcome back to lesson 3.1. Hopefully you've had a chance to look at the previous video, which was an introduction to related rates. In that video we reviewed implicit differentiation and other rules of differentiation such as the power rule, the product rule, and the chain rule. And we looked at how we could model some physical and geometric situations using the Leibniz notation for derivatives in calculus. If you've not yet watched that video, I would encourage you to go back and do that, because a lot of the derivatives and rewriting into notation that we did in that video, we are going to take for granted and make use of in this video as we look at how to take apart some word problems and do some calculus to solve them. So if you've not yet watched that video, please go ahead and do that, and then I'll see you back here. Otherwise, let's take a look at a few quick notes that we need to review and expand on. The first thing that I want to talk about is the Leibniz notation itself. The derivative dy dx of a function, y equals f of x, is its instantaneous rate of change with respect to the variable x. So this, you may remember, is the IROC, the IROC. It's the slope of the tangent line of a curve. But let's make it a little bit simpler than that. You'll notice that dy dx is written as a fraction, but this isn't really a fraction any more than writing a speed of, let's say, 25 miles per hour would be a fraction. So miles is not part of a whole hour. This is a comparison of two units in this case. We can also have a comparison of two numerical values. It is a ratio or a rate. This is exactly what slope is. If you think back to Algebra 1, we looked at straight line equations and we saw that slope was a change in y as a function of the change in x. In other words, m equals delta y over delta x. And if you take the delta and just replace it with a d, what you have is Leibniz's notation. These minuscule infinitesimal changes here, these are your differentials. And so the differential of y with respect to x. All right, a couple of more notes here. So when a function describes either position or distance, the rate of change is going to be interpreted as velocity. Now, this is important. Velocity is different than speed. You may recall that speed is the absolute value of velocity. It is the number. Velocity, however, indicates magnitude and direction. And the way that we do that in calculus is by looking at a signed value on a number line. And so we can have positive and negative velocities. Also, a time rate of change will always be answering some form of this question: how fast is a quantity changing? So these are words that we want to look for. A couple of examples. If V is volume changing in time, then dV dt is the rate, or how fast the volume is changing with respect to time. Now, back to this idea of velocity being a signed value. There are some standard practices that you don't have to adhere to necessarily, but would give you a constant framework that I think would be helpful in translating some of these problems, and would also make your work easy for others to follow. In particular, you want to make the work as easy as possible for the AP exam grader. You want to make that person your best friend. So make their job easy for them. So one convention that we have is this. Let's say that we have a street lamp. So I'll draw an old-fashioned street lamp. And we've got a person who is walking towards the lamp at a particular rate. So if a person is walking toward a street lamp at a constant rate of 3 feet per second, then we know the distance is decreasing. And so since this is a decrease in distance, it's a decrease in the absolute value of that distance, we're going to use a negative 3 feet per second. Now, notice that I drew my figure in such a way that he's moving right on what could be considered an x-axis. So if it helps you, draw the picture the other way. But we're going to think about this in terms of the rate itself, since that's where we're going with this. So if the rate is a positive value, if it's an increase in distance, then it's going to be positive. But if it's decreasing, it's going to be negative. And so although the person may be moving in a positive x direction, the slope of the line indicating the rate of change is negative. So the word that you're looking for here is decreasing, and that corresponds to the sign for your rate of change. Now, if they walk away from the lamp, the distance is increasing. So same situation here. In this case, notice that as the person walks away from the lamp, the x value, the distance between them, is increasing. And so that increase corresponds to a positive rate change. Lastly, before we get started looking at some examples, here are some guidelines for solving the related rate problems. This is just a standard set of steps that you can go through to turn a word problem into a calculus problem that you can solve. The first thing is make a sketch and label the quantities. Step 2, read the problem and identify all of the quantities as know, given, and find. Now let me stop for a minute and say something about these two. These are the types of things that especially we smart math students want to blow off and skip and jump right into writing an equation. And I know all about this because I struggled with this myself. I want to just get straight to writing an equation. And here's the thing. Not only is it easier to get to the equation if you take the time to do steps 1 and 2, but again, you are really being kind to your AP reader, because that person is going to be able to see exactly what your thought process is because you spelled it out for them. And even if you make a mistake setting up your equation, you get partial credit now because you have carried them with you on your journey of problem solving. Next, this is the calculus. Use the chain rule. Use implicit differentiation. And since we're looking at rates, this is almost always going to be with respect to time. Number 5, after you've completed step 4, go back and substitute into the resulting equation all known values for the variables and their rates of change, and then solve to get a numerical value. Now, if it is a decimal value or an irrational value, maybe it includes pi or something, you're going to want to report those rounded to no fewer than 3 decimal places. And again, that's per the guidelines on the AP exam.